Hello, my name is Frank McQuillan from Pivotal, and together with my colleague Bharath, it's a pleasure to speak with you today about machine learning, graph, text, and geospatial on Postgres and Greenplum. Advanced analytics in its various forms is rapidly growing in importance in enterprise computing. And since key enterprise data typically resides in relational and document form, it is suboptimal to copy data between different systems in order to perform analytical operations. Greenplum is able to run both traditional and advanced analytic workloads in database, things like machine learning, graph, a variety of data science productivity tools, geospatial, text, and data transformations. And it's this integrated capability in Greenplum that greatly reduces the cost and the silos created by procuring and maintaining multiple tools and libraries. So in this presentation, we'll give a tour of these Greenplum capabilities, review some scalability results, and also talk about recent use cases. So these are the topics that we're going to cover, starting with machine learning and ending with a look ahead to 2018 work. Okay, let's start with machine learning with Apache MADlib. Now, MADlib is an open source SQL-based machine learning library. It is a top-level project at the Apache Software Foundation, and it runs in database in both Greenplum and Postgres. And the idea is of bringing machine learning to the database is that you don't need to move data out of the database, run it in a separate execution engine, and move the results back. And really the main advantage of MADlib on Greenplum is machine learning on large data sets. So this means a focus on scalability and performance. The MADlib project started in 2011 by a bunch of EMC Greenplum architects and Professor Joe Hellerstein from the University of California, Berkeley. And since that time, we have also had participation from Stanford University, University of Wisconsin-Madison, University of Florida, and it has really been a great collaboration between industry and academia. There are more than 50 machine learning, graph, math, and stats functions in MADlib. You may see some that you recognize here, things like logistic regression, decision trees, neural nets, k-means clustering, etc. It is a comprehensive and mature data science library, and we've seen it used to solve for a whole variety of real-world use cases. So why MADlib on Greenplum? Well, it's all about distributed computing. Better parallelism in the sense that the algorithms are designed to take advantage of the parallel processing architecture of Greenplum. So you can run a single massive model in parallel. And you can't do that in single node Postgres or in a lot of other vendor and open source tools because you run out of memory on a single server. Better scalability, the algorithms scale in a predictable manner with the data set size and the mean parameters of the algorithm. So we think a lot about how an algorithm will scale when we build it in MADlib. Higher predictive accuracy. This means you can use all the data, not just a sample of the data. And our data science colleagues tell us that they want to use all the data because even if you have a large data set, for example, high cardinality dimensions like user ID, you can end up with sparse data for a particular user. So data scientists want to use as much relevant data as possible. And as I mentioned, it's a top-level ASF open source project, and ASF is really a great place to develop open source software. This is the well-known architecture for Greenplum Database, showing the distributed nature of the master talking over interconnect to multiple segment hosts or worker nodes. Apache MADlib is a library of methods that reside in the database server that can be invoked using the SQL interface. And these methods consist of a mix of user-defined functions, user-defined aggregates, and user-defined types. The algorithms themselves are generally implemented in C++ for performance reasons, but we also use Python and SQL as well. And I would note that MADlib is part of the database fabric. So this makes it easy for database administrators to deploy and manage, since it's not a separate daemon or separate software running outside of the database. Now the learning curve is relatively modest because it is a familiar SQL interface. So let's take an example here. Let's say we're real estate agents or a website such as Zillow, and we want to predict house prices in our area based on historical data. So first we train a model, which means we build a predictive model from historical data using features such as property tax, number of bathrooms, and the size of the property in square feet. And we also group by bedrooms here. And what that means is that we're running a separate model for each bedroom in the house. And probably zip code would be a better choice for that if you want to run different models for zip code. So after we have a model, we do prediction. And prediction means using the model that we have built to predict house prices for new data that we haven't seen before. So we have a select function to call the prediction function, called predict, and the result is that we have a predicted price showing on the right-hand side here, which is the result of from the model. So this will help us in pricing decisions that we need to make for our business. But does it scale? Well, MADlib is on Greenplum is really built for scalability, and this is an example of an algorithm called support vector machines, which is a classic algorithm for classification, regression, and novelty detection. So here on the x-axis, we're seeing size of data. So we've done this run with 1 million, 10 million, and 100 million rows in the table. And the y-axis is runtime. And what we're seeing here is linear scalability with data size, which is what we want. So this is running on a relatively small cluster of 1 master and 4 segment hosts. The absolute values are not that important. What's important is the trend showing this linear or sublinear scalability. And that gives us some confidence that as our data set grows, then the runtime will grow in a predictable manner. It's not gonna blow up on us. Now let's talk about data transformation. Data scientists tend to spend an enormous amount of time preparing data for input into predictive algorithms. So they need tools to make this as efficient as possible. Well, by virtue of the Postgres heritage, there's a rich library of native functions and operators, including array functions, aggregate functions, and window functions. And also keep in mind on Greenplum, these are running in parallel on a cluster of many Postgres instances. So let's look at an example of a window function. So in this window function, what we're computing is the average price over a partition of, in this case, it's a group name. So either laptop, smartphone, phone, or tablet. So with a very simple select statement, we're able to figure out what average price is for all of the products in a particular group. And I would refer you to this blog post on comparing window function features by database vendors. And this is a comparison of 10 or 20 different open source and commercial products, comparing things like window functions, and it really shows Postgres at the top of that list. And in addition to the Postgres capabilities, Apache MADlib provides a number of data transformations to aid in this work as well for very large data sets. So some of these may look familiar to you: pivoting, sessionize, encoding, But I would like to elaborate on path functions as one example. Path functions are useful in a variety of different applications, including predictive maintenance, customer churn, securities, trading analysis, and this example, which is from e-commerce. So let's say we have an online store that sells beverages, wine, beer, juice, and soda, and the like. And we would like to understand more about the purchase behavior for wine and beer. And in particular, we want to identify regular quick shoppers who spend a lot of money on our site. And the reason we want to do this is because this may help us shape our loyalty programs and personalization for these important buyers. So how do we do that? Well, this is the raw data we have from our website. A beacon fires events to a log file whenever a shopper visits pages on our site. Landing page, a wine selection page, checkout page with associated revenue. It's time-stamped. I have a user ID here. But how can I query this data to answer the business question that I have about my valuable quick shoppers? Well, what would the steps be? First thing we need to do is order and partition our data. So SQL can do that. That's reasonable. But after that, we need to, for each of the ordered partitions, look across those set of rows and extract the matched patterns. And once we have these matched patterns, in our case, this was quick shoppers, we want to do something with that. We want to count them or aggregate, do an aggregate function, run a window function, etc. So this is a pretty complex set of operations. It involves doing complex pattern matching across rows, not just within a row. And it's not something that's easily supported by SQL, even if you wrote a lot of SQL. So what you could do is use a MADlib path function, which is shown here. So this is a single select statement, which has parameters for partitioning and ordering the data. It has symbol definitions, and a symbol is just a thing of interest in a row. In our case, we're defining a bunch of symbols based on the page that the online shopper is at. And we define a pattern match across rows. So here we're using familiar Postgres pattern matching. This is a POSIX regular expression. You could use like or similar to pattern matches as well. So what this regular expression is saying is that starting from a landing page, going to any two other pages, and then making a purchase. That is kind of the pattern that we want to extract. And we could also put a time-based thing in here as well, saying the shopper needs to check out within, say, 2 or 3 minutes. And based on that pattern match, then we want to sum the revenue. And if we do that, then we've identified a data set here. We have information to understand who our quick purchasers are, how much they spend, and then I can cater to them in the right way to increase what they spend on my site and hence improve my business. So even if you could write the SQL to identify these quick shoppers, it would be very hard to make it performant for very, very large data sets. And we've implemented this primarily in C++ so that it scales across the cluster for extremely large numbers of transactions in the billions. Now let's shift gears a little bit and speak about graph analytics. The motivation behind adding graph to Greenplum is, as before, to bring compute to where the data resides. We're trying to avoid the case where you have to procure and manage a separate graph database product. And in addition, many practical data science problems are solved with an ensemble of models, graph being just one of them. So if you can do graph in the same place that you're running regression or clustering or other algorithms, then it is convenient and less expensive. Brief introduction to graphs. Graphs can help us understand things like connections and relationships. Graphs can be very small, like this group of friends, But many real world graphs are very large, like this social network. And in things like fraud detection, there can be hundreds of millions of transactions involved. And if you think about route planning, the road network is very large and complex. So we need a computing platform that allows us to efficiently reason across very large graphs and to do analytical operations at scale. Here's what a graph looks like if you zoom in on it. In this case, it's a directed graph. There are vertices, or nodes, as some people call them. There are edges connecting them. And the edges can have direction, and they can have weight. And the weight could be negative. So for example, in the case of vehicle navigation, the vertices could be road intersections. The edges could be the roads connecting those intersections. The direction could be the allowed direction of travel for the vehicles. And the weight could be the distance between the intersections, or perhaps the travel time. In Greenplum, using MADlib, graphs can be represented by standard relational tables. So you don't need a bespoke graph storage model. There's a vertex table, which lists the vertices and associated parameters. There's an edge table that lists source and destination vertices to give direction, edge weight, and other edge parameters. Let's look at an example. Many of you may have heard about PageRank in reference to web search. It's a link analysis algorithm that measures the importance of a vertex in a graph by counting the number and quality of links to that vertex. I was surprised in the number of applications of PageRank. For example, in neuroscience, PageRank of a neuron in a neural network has been found to correlate with its relative firing rate. The way to run a PageRank is with a simple select statement. I select PageRank, I specify the vertex and edge tables and the output table, and that's essentially it. So then I get an output of PageRank by vertex ID. Now you could implement your own PageRank in SQL, but it would be a project, and also you'd need to do performance testing to ensure that it scales to very, very large graphs. Like most Apache MADlib algorithms, there's a lot of default parameters, but if you want more control, you can specify additional parameters. In this case, things like stopping criteria or personalization vertices for something called personalized PageRank. So I asked about scalability a brief time ago. So this is a log-log graph. It shows graph size on the y-axis going up to 100 million vertices. And for each vertex in this example, there's an average of 50 edges. So what that means in the top right here is 5 billion edges. So this is a graph of 100 million vertices, 5 billion edges, running on a small cluster, again, of 4 segments, 4 worker nodes. And this is the runtime. So the key thing here is linear predictable scalability or sublinear scalability with graph size. So this is really what we want to see. And many other open source and commercial graph databases can't scale like this because they're not built as distributed systems in the way that Greenplum is. Now let's talk about data science productivity tools. First of all, R. So Pivotal R is an R interface to MADlib. So what it allows you to do is, in the same way that we had SQL code here to call linear regression, you can run R code and call linear regression. So you can develop your R code on your client machine here, using R libraries and things that you're familiar with. Then when you call a Pivotal R function, it actually converts that into SQL, passes it to the database, where it runs on the parallel database. That's where the data is, and then it returns the result set back to the client machine. So the whole idea is that you're not moving data. The data doesn't leave the database. And it's only the strings of SQL and the model output that are transferred across the interconnect. Let's stay with the theme of multiple language support. Postgres has a procedural language extension that allows you to write functions in Python, R, C, SQL, Java, SQL, or Perl, and to call these from SQL. So these functions are invoked during query execution, and they run on each segment in the database in a data parallel manner. That is to say, independently on the data that is distributed to that segment. And this is very useful because it allows you to develop in the language that you like and are comfortable with. It promotes code reuse, and it also allows you to take advantage of the many great libraries that are available in these languages, such as these: scikit-learn, pandas, XGBoost, TensorFlow, etc. So Pivotal offers a data science bundle, which includes 100+ libraries in Python and R that you can use when you're writing user-defined functions using the procedural language extension that I mentioned on the last slide. This is great because it really makes it easier to deploy. You can deploy, say you have a very large cluster of 100 segments. With a single command, you can deploy all of these libraries to all of the, across the entire cluster, and then keep up with the latest versions. And one example of this I can think of as a Pivotal customer who's an educational institution that runs many XGBoost models at a time on their cluster related to improving student outcomes and experience. So these aren't huge models because each model runs in a single segment, but they have many, many of them. So they can do their training using XGBoost in parallel at the same time. PL Python and PLR do suffer from a security problem because they run as untrusted languages. And this means that only privileged users are allowed to create user-defined functions, because a Python and R function can access internals of the database server process and gain OS level, operating system level access with permissions of the server process. So this restriction to privileged users is really inconvenient for data scientists who are trying to train and debug models, develop models. So PL Container is a way of sandboxing the execution of PL Python and PLR in Greenplum so that user-defined functions run inside of a Docker container. It effectively restricts interactions with the environment and allows non-privileged users like data scientists to create and deploy user-defined functions in these languages. And I would refer you to another presentation by my colleagues Hubert and Jack, who go into PL Container in much more detail. So finally, on the data science productivity side, Greenplum supports the two most popular data science notebooks. On the left is Jupyter notebooks, and on the right is Apache Zeppelin. So you can develop your data science models with these two notebooks in SQL, Python, and a mix of languages using very large data sets living on Greenplum. Before I hand it over to Bharath, the last topic I'll cover is geospatial. And there's a wide range of use cases in the physical world, from scales like circuit boards to autonomous vehicles to global transportation. PostGIS is a spatial database extension which allows for analysis and processing of GIS objects. So PostGIS allows you to represent these objects in a relational database and to query them very, very efficiently. So in the case of Greenplum, we're talking about being able to query not just millions, of these objects, but billions of geographic objects. And by objects, I mean, for example, in the vector world, things like points, lines, polygons, curves, etc. And in the raster world, there's native base types in PostGIS for storing and analyzing raster data from things like images or video. Spatial joins are really the bread and butter of spatial databases. They're similar to the joins that you may already be familiar with in a relational database, but they operate on these geospatial objects. So they allow you to combine information from different tables by using spatial relationships as the join key. For example, do two lines intersect? Do two polygons overlap? And here's a list of some of these kinds of relationships. So much of what we think of as standard GIS analysis can be expressed as spatial joins. And in this example, we have two kinds of geometric objects. We have subway stations in New York, which are points, lat longs on a map, if you will. And the neighborhoods are polygons. And the query that we're trying to do here is to identify all of the subway stations in a particular neighborhood, in this case, Greenwich Village. So you have a single select statement here, and you can see we're doing ST contains. And the ST contains identifies the subway stations that are enclosed by the polygon representing the neighborhood, where the neighborhood name is Greenwich Village. This is an example from the Boundless workshop, which I would highly recommend. And this is a tiny data set. Spatial indexes are what make spatial database for large data sets possible. So PostGIS has a way of indexing these data structures and being able to query them very effectively without having to do sequential scans for every record in the database. At this point, I'd like to hand it over to my colleague, Bharath, to continue with the rest of the presentation.
Thank you for that introduction, Frank. So to continue, as my good friend Billy Mays would have said, but wait, there's more. So we'll continue by talking about text and text analytics on Greenplum. First, let's take a step back. When we look at the state of unstructured data, most of the industry experts agree that about 80 to 90% of the world's data is unstructured. Yet only about 0.5% is effectively analyzed and used today. If we actually use this customer-related text data, whether it's in emails, chat records, documents, etc., if we can extract this text, we can extract valuable predictive insights, and it only takes seconds. So what we ended up doing was building GPText. GPText essentially combines Greenplum Database with Apache Solr, and by extension, we have to offer some integrations with MADlib, which I'll talk about later. It's the only database that actually integrates text at scale. What we do is we can actually combine semi-structured and structured data and index it and search through it using the Apache Solr libraries, and we can process these massive quantities of raw text for large-scale analytics using Solr and MADlib. But it's all exposed as SQL UDFs. So you get the flexibility and configuration that you would get with Solr, but you get the familiar SQL interface and the scalability that you do with the GPDB architecture. When we look at a GPText index, it's processed for efficient storage. We leverage the Solr indexing capabilities and are able to store the word, the position, any particular synonyms where words are equated to one another. We're able to stem the words accordingly, and we're also able to figure out relevancy. And by extension, we also added some capabilities to process emoticons and URLs. So this is used for fast search, where the search data is indexed and you don't have to do a scan through the whole data. And it's processed efficiently so you can return your relevant results by weighting the results that matter to you. If we take a look at the index on the right side in the picture, you can see that we use an inverted index, where the words are stored in this tree-like structure, and you have the positions, or the document names and the positions stored for each word. So for example, if we take a look at the word group, we can see that it's stored in document 1 at position 99 and 199, document 4 at position 55 and 88, and so on and so forth. So this allows us to easily calculate the term frequency in a particular document, how often a particular word appears across all the documents, as well as the relevant data that I mentioned previously. This is used for essentially fast search and fast indexing. Now, when it comes to documents, there are various different document formats. They're not standard. You have documents that have international text, documents that have social media, log analytics, etc. And so you would need to use different analyzers to process each different type of text. And this is where analyzer chains come in. What an analyzer chain is essentially a tokenizer followed by a series of filters to process your input text and output the tokens into your GPText index. So a particular tokenizer that you might use is the white space tokenizer, but there are various other ones to help process social media or URLs or geographical coordinates, etc. And then you can use a series of filters such as removing common words, such as stop words, being able to stem words to a common root, being able to equate particular words to one another, so finding synonyms. And this is all highly customizable using the GPText configuration interface. So essentially, you can parse and extract your data without losing meaning at all. On the other side, when we look at search, we're designed to be able to support multifaceted queries, such as Boolean queries, proximity searches, and even wildcard searches using various query parsers. When you look at different text search and text analytics packages, they do offer these capabilities, but you have to write your queries separately and use a series of joins or complex series of correlated queries in order to actually figure out what you're talking about if you're trying to write a compound type of query using different query parsers. So there's no need to write that. You can actually write it all as one single query using the different types of parsing formats, whether it's a Boolean query or a surround query or complex query, and we'll take care of the heavy lifting behind the scenes. So essentially, this supports an almost Google-like syntax to be able to write these complex queries and get the relevant search results you need. By extension, GPText also stores all this metadata, so the terms, the document positions, as well as the word positions within the document and other information, and we can expose this data to MADlib. And this can be used for various capabilities such as topic modeling or clustering, or even sentiment analysis, or in the case of log analysis, you can use it for sequence pattern mining. And so we can expose this to MADlib for further analysis. Now, your data is not always stored within Greenplum. Sometimes it might be in raw documents such as PDFs or Word documents that are stored on external file systems such as HDFS or FTP or S3. What we offer is the ability to connect to these external data sources and directly extract and process your raw text data and store that as an index in GPText. So we use Apache Tika, which is built into the GPText and Solr packages. And you can extract the text and you can, whether it's a PDF document, Word document, an email, a PowerPoint, etc., and you can store that raw index. And then when you search on the index, you're able to refer back to the original document. And this way you can essentially access and search your data no matter where it is and no matter what format it's in. Now let's take a look at the connectivity features that Greenplum offers. So many data scientists and many customers are looking towards using Spark. And they have a lot of different data scientists, and we want to leverage the Spark skill set that these different data scientists might have. So what we do is we provide data access to Greenplum data, where you can essentially offload your data onto your Spark cluster, use these off-cluster resources to do computations using the Spark algorithms and Spark library, and you can push the result sets back into Greenplum for further storage. And so this essentially allows you to leverage your skill sets, and be able to use Spark as an external library or external package rather than relying specifically on the Greenplum tools. We also offer a Greenplum Gemfire connector. So Gemfire is the in-memory data cache layer that's built for fast transactional processing. And essentially you can process incoming data and write that in batch to Greenplum. And then you can use Greenplum for the heavy modeling and lifting in order to generate your analytical models. And you can push that result set back into Gemfire for use in further analysis. So this way you get the fast transactional layer or processing that you would with Gemfire, but you get the heavy analytical lifting being taken care of by Greenplum. Now let's take a couple looks at different use cases that we have involving the different analytical tools that we have for Greenplum. So here we have NICT, which is the transportation and weather response arm for the Japanese government. So they have a lot of different data sources that are coming from various sensors around the country, as well as social network service data, either geotagged Twitter data or Facebook data that's coming from various users. And historically, they weren't able to process this data to develop effective response plans to natural disasters that might be occurring, such as freak rainstorms or earthquakes that might be happening. By pushing all of their data onto the Greenplum stack and using the analytical tools, they're able to easily model data from these heterogeneous data sources and more easily develop response plans for these different natural disasters. And they're able to effectively respond to them and provide guidance to their citizens easily. So here we have a cybersecurity use case. So this is logs that are collected from Active Directory activity, server information, as well as LDAP activity. These logs are then stored on external data sources that are accessed via Greenplum through external tables. And by using the full suite of analytical tools provided by Greenplum, we're able to develop an ensemble model, such as regression, user behaviors, and graph model. And by using this, we can actually develop a particular score for a user, an aggregate score. And this can be used to determine whether a user is going through normal user activity or whether they might be an anomalous user. So if we dig into this graph model, we can see what types of typical user behavior might be happening. So in a typical use case, you might see this machine on the left side accessing these particular machines in this particular order. And anomalous behavior might be if this regular user laptop is accessing, for example, a database with financial information. And by looking at the historical graph trends and how different machines access each other, how often, and which machines access each other, you can tell what regular user activity might be and how to differentiate it from this particular anomalous user activity. Now, when we look ahead, we can see, we revisit this slide where we show the different capabilities that are offered through Greenplum, such as the text analytics, graph analytics, and traditional BI tools. In the future, what we want to do is essentially improve upon the performance of these existing tools, as well as add new features and capabilities to these individual tools. But we also want to provide a fully integrated experience for our customers by improving the workflow that a user might have from loading the data into Greenplum and using these modeling tools to transform the data, and then using the modeling tools to be able to extract the valuable insights that they might need for their different use cases. Thank you.